How was the famous WOW signal first detected and documented? Why has the WOW signal remained unexplained despite decades of follow-up observations? In the silent depths of a moonless night, the universe stretches out above, vast and enigmatic. The sky is a tapestry of faint stars and distant galaxies, each a tiny beacon in an ocean of darkness. Yet, hidden among the steady pinpoints of starlight are fleeting flashes and whispers that defy understanding. These are the cosmic mysteries, brief flickers of energy and light, bizarre beacons from the far reaches of space that have left astronomers both awestruck and puzzled. As we begin our journey through these unexplained phenomena, we drift gently into the realm of the first enigma, sudden bursts of radio waves from deep space, appearing without warning and vanishing just as quickly. It begins without any fanfare. A telescope's receiver trembles with a momentary surge of noise. In an instant, a burst of radio energy washes over the Earth, then is gone. These events are known as fast radio bursts. Each one lasts only a few milliseconds, an eye blink on cosmic timescales. But in that brief moment, a fast radio burst can unleash as much energy as an entire galaxy shining for a year. One moment the sky is calm, and the next, a burst of radiance flashes by, as if a distant lamp in the universe has flickered on and off. Fast radio bursts, or FRBs, were only discovered recently in our exploration of the cosmos. The first was identified by chance in data from a radio telescope just over a decade ago. At the time, it was so unexpected that astronomers weren't sure if it was a real cosmic signal or a fluke of instrumentation. But as more of these bursts were detected in the years that followed, it became clear that they were indeed real, and surprisingly common. They arrive from all corners of the sky, unpredictable and dispersed across billions of light years. Dozens, now hundreds, have been recorded. They pop up like brief camera flashes in a dark stadium, here and there, with no pattern that we can yet discern. What could possibly create such intense, split-second blasts of radio waves? The truth is, no one knows for certain. The leading theories point to extraordinary events or exotic objects. Some scientists suspect that the culprits might be magnetars, neutron stars with ultra-strong magnetic fields that can release gigantic bursts of energy. Others suggest colliding neutron stars or black holes merging in distant galaxies, sending out a final scream of radio energy. There are even more fanciful ideas. Perhaps the flashes come from cosmic strings, hypothetical defects in the very fabric of spacetime, left over from the universe's birth. A few have even wondered, in hushed speculation, if these bursts might be interstellar messages, or the distant signatures of technology far beyond our own. For now, all of these ideas remain conjectures, shadows of an answer. One of the few clues came when a fast radio burst was traced to a source in a tiny, far-off galaxy. That particular burst repeated itself several times, allowing telescopes to pinpoint its home. To astronomers' surprise, the source was not at the heart of a large galaxy or near a supermassive black hole, as some had expected. Instead, it was in a humble dwarf galaxy, billions of light-years away. In that faint galaxy, the culprit could be a highly magnetized neutron star, perhaps the shattered remnant of a once massive star, periodically flaring with energy. In another case, an unusually powerful fast radio burst was found emanating from a cluster of ancient galaxies far across the universe, a neighborhood previously thought unlikely to host such eruptions. Each new detection seems to carry its own hint, its own contradiction, and each deepens the puzzle. Even our own Milky Way offered a tantalizing hint recently. In the spring of one year, a known magnetar within our galaxy suddenly spat out a burst of radio energy that, had it come from a neighboring galaxy, would have looked very much like the fast radio bursts we see from afar. For a brief moment, that magnetar became a miniature version of the mystery. This event suggested that at least some FRBs might indeed be magnetars, unleashing their fury in a sudden crackle of radio waves. But magnetars in other galaxies would have to be far more energetic than any we've observed up close, raising questions about how they could release such titanic blasts without tearing themselves apart. Listening for these bursts is a bit like straining to hear a pin drop in the middle of a storm. Radio noise from both the cosmos and our own human technology constantly washes over the airwaves. Amid that cacophony, an FRB arrives as a crisp, sharp clap from the cosmos, fleeting and faint by the time it reaches us. Astronomers must sift through mountains of data and static to find these millisecond miracles. When one is found, it appears as a sudden spike on a data chart, a bright blip against background noise. It comes with a telltale signature. The burst's high-frequency radio waves arrive just moments before the low-frequency ones. This effect, like a prism spreading out colors of light, occurs because the radio waves are dispersed by the tenuous gas they traverse in intergalactic space. From that tiny difference in arrival times, scientists can calculate an immense distance. Often it turns out the burst began its journey billions of light years away. Such distances confirm that whatever produced the FRB must be astonishingly powerful. The distances involved are truly staggering. Many FRBs hail from realms billions of light years distant, meaning the signals we intercept now have been traveling for a significant fraction of the universe's lifetime. We are, in essence, catching whispers from the deep past. When a fast radio burst reaches us, it is as though an ancient event, one that unfolded long before humans walked the earth, has sent a brief hello across time and space. It is humbling to realize that some of these flashes occurred when the cosmos itself was young, and only now are we witnessing the after effects. Yet for all their power, they remain elusive. Most known FRBs have been heard just once and never again. A rare few do repeat, but even those do so irregularly, with pauses that can last days, weeks, or months before another burst suddenly comes. Without a clear pattern, we are left guessing at what could be happening in those distant reaches to trigger such outbursts. Are they like cosmic volcanoes, building up pressure and erupting unpredictably? Or are they spinning objects flaring on and off like cosmic lighthouses shrouded in fog? Each possibility raises new questions. In a quiet field under a canopy of stars, a solitary radio dish can listen patiently to the sky. The night air is cool and still. There is only the soft crackle of static from a speaker, blending with the rustle of wind in the grass. Suddenly, a sharper hiss cuts through the background noise. It lasts barely a heartbeat, but it is unmistakable, a real signal from somewhere deep in the cosmos. In that instant, beneath the vast dark sky, one realizes that a powerful event has unfolded in a far-off galaxy, and its echo has traversed the light years to reach this little listening post on Earth. That sudden, transient burst of sound from the speaker is what it means to catch an FRB, a fleeting hello from a mystery beyond our reach. As things stand, fast radio bursts remain one of astronomy's great unsolved mysteries. With each new telescope array built to scour the skies, some with dozens of antennae poised to catch these split-second signals, we are finding more and more of them. We carefully catalogue their properties. One burst might last slightly longer than another, or exhibit a different mix of frequencies. We notice patterns that tantalize us for a while, only to find exceptions that break those patterns just as quickly. Bit by bit, the evidence accumulates. Someday, with enough pieces, the full picture may emerge, and we might finally understand the engines behind these bursts. But right now, each FRB is a reminder of how little we know. It's a cosmic tease, a brief flash saying, "I am here," without revealing its identity. Our journey now moves from these transient radio flashes to another singular signal that once rattled the airwaves, a signal so curious that it has kept people wondering for nearly half a century. Decades before, fast radio bursts became a topic of intrigue. A lone radio telescope in Ohio detected something extraordinary one summer night. The year was 1977. The signal it found was so strong and so unusual that the astronomer on duty scribbled a single word next to the recording: "Wow." At the Ohio State University's Big Ear Radio Telescope, on the night of August 15, 1977, the sky was being surveyed for any unusual radio signals. For the most part, it was a routine night of data, a steady stream of numbers and letters printing out on paper as the telescope quietly scanned the stars. But then, in the early hours, a particular set of characters jumped out from the endless columns of data. It indicated a very strong, focused radio signal, unlike the typical background noise. When Jerry Amon, a volunteer astronomer reviewing the data, saw the anomalously high reading, he was astonished. In a moment of excitement and disbelief, he grabbed a red pen and circled the number code on the printout, scribbling one exclamation beside it: "Wow." The signal was indeed worthy of the exclamation. It was a narrowband radio signal, meaning it occupied a very specific frequency rather than a broad spread. In fact, it was centered near 1420 MHz, a frequency naturally emitted by hydrogen, and notably, a frequency that some scientists had guessed an extraterrestrial civilization might choose for interstellar communication. The signal was intense, far stronger than the ambient noise of space that Big Ear usually picked up. It rose and fell over a span of roughly 72 seconds, the length of time the telescope's fixed gaze swept past that point in the sky, and then it was gone. In that brief window, Big Ear had heard something extraordinary, something that to this day defies full explanation. They called it the wow signal, after Amon's amazed annotation on the sheet. Here was a cosmic whisper that shouted, for just a minute, and then fell silent. Astronomers around the world were intrigued and perplexed. If this was a signal from an intelligent source, perhaps another civilization's beacon or a distant spacecraft, it was one of the most thrilling discoveries imaginable. If it was a natural phenomenon, it was something entirely new and unexpected. But to investigate further, scientists needed it to happen again. And despite many attempts, the wow signal has never reappeared. For months and years after that night, researchers re-examined the data and pointed their radio dishes back at the same patch of sky. The region in question lies in the constellation Sagittarius, not far from the dense star fields near the center of our galaxy. But every time they listened, there was only the usual static and the occasional hum of terrestrial interference. The mysterious signal, whatever it was, did not repeat. It was as if someone had briefly spoken a word or two in a silent library and then vanished without a trace, leaving everyone to wonder if it had been real or just imagined. Over the decades, numerous hypotheses have been proposed. One idea was that perhaps the signal came from an earthly source that just happened to reflect off space debris or the moon, mimicking a cosmic origin. However, the specific characteristics of the wow signal, its frequency, and how it peaked, didn't match typical terrestrial interference. Another hypothesis involved comets. A scientist suggested that a passing comet with a cloud of hydrogen around it could have emitted at the hydrogen line frequency, causing a spike in Big Ear's readings. Yet, when comets were later searched for in that region during similar conditions, nothing like the wow signal was detected. Others speculated it could have been an unusual astrophysical burst from a star, or even a black hole. But no definitive source was ever found. In the absence of a clear explanation, the possibility of an artificial origin, that is, an alien transmission, has lingered in people's minds. The WOW signal remains one of the strongest candidates for a signal from extraterrestrial intelligence, simply because no natural explanation fits perfectly, and it was so singular and strong. Of course, extraordinary claims require extraordinary evidence, and one signal is far from proof of alien life. Jerry Amon himself was cautious, expressing doubt that we had heard ET. But the allure of that interpretation has fueled imaginations and further searches for years. What makes the WOW signal especially haunting is its loneliness. It came only once. In all the years of scanning the heavens since, with far more sensitive equipment than Big Ear had in the 1970s, nothing quite like it has been heard again. It stands alone, a cosmic question mark. Perhaps it was a fluke of nature, or an equipment glitch that just mimicked a real signal. Or perhaps it was truly a call from the dark, a call that we happened to be lucky enough to catch, but that might not repeat for centuries. If it was a greeting from another intelligence, maybe it was sent as a beacon, and we just stumbled across it. Or maybe the beacon switched off, or the civilization that sent it long ago is now gone. We simply don't know. Even today, when astronomers conduct new SETI, search for extraterrestrial intelligence, experiments, they often include the coordinates and frequency of the WOW signal in their observations, just in case that mysterious voice in the void speaks again. So far, each time has yielded only silence, as if the stars remember speaking only that once. And so the WOW signal remains, true to its name, an enduring wow in the annals of astronomy, a one-time cosmic enigma. As we ponder that singular burst of radio waves, we turn our gaze to other, more persistent mysteries. Not all of the cosmos's baffling phenomena are fleeting whispers. Some are blazing beacons that shine across billions of light years, drawing attention with their incredible brightness. Our journey now moves from a strange moment in the 1970s to discoveries that began in the 1960s, when astronomers found lights in the depths of space that were too bright, too powerful to be stars, and far more distant than anyone expected. These beacons are known as quasars, and they challenged our understanding of the universe with their almost unimaginable energy. As radio astronomy opened new eyes on the universe, researchers stumbled upon peculiar objects that defied easy explanation. They found intense radio sources in the sky that, when optically identified, appeared to be nothing more than faint star-like points of light. One by one, these sources were catalogued, and they carried names like 3C273 and 3C48. At first glance, they looked like ordinary dim stars in telescopes, but their light hid a startling secret. When astronomers spread that light into a spectrum, they saw patterns of emission and absorption lines that were bizarrely shifted in wavelength. So shifted, in fact, that it implied these objects were incredibly distant, billions of light years away. If that was true, then to be visible at all from Earth, they had to be unleashing as much energy as an entire galaxy of stars, concentrated in a space no larger than a single star. The term they coined for these mysteries was quasar, short for quasi-stellar radio source. They were quasi-stellar because they looked star-like, yet their energy output was anything but stellar. Imagine a single point of light outshining a trillion suns. That is what a typical quasar does. They shine from the cores of galaxies so far away that their light has been traveling to us for billions of years. In fact, when we observe a quasar, we are often looking deep into the past, seeing the universe as it was when it was young. Quasars are like cosmic lighthouses from a bygone era, their brilliant beams crossing the eons to reach us here and now. In the heyday of their discovery, quasars upended the understanding of many astronomers. How could something so small appear so bright? Some even wondered if the laws of physics were different in those distant realms, or if these objects were perhaps not as far as the redshift suggested. But as more data poured in, it became clear. Quasars were real and cosmologically distant. They were among the brightest objects in the universe, and they marked the locations of supermassive black holes feasting on matter in the centers of newborn galaxies. Today, we understand that a quasar's power comes from a disk of gas and dust superheated as it swirls into a giant black hole. As matter spirals inward under gravity, it compresses and heats up, releasing tremendous radiation. It's a bit ironic that the darkest phenomenon we can imagine, a black hole, which by itself emits no light, can lead to one of the brightest beacons in existence, thanks to the material surrounding it. The energy that quasars emit can be mind-boggling. In just 1 second, a typical quasar can release more energy than our sun will emit in millions of years. All of it pours out from a region of space not much larger than our solar system, at the heart of a galaxy tens of billions of light years away. Quasars also carry with them the story of the early universe. The farthest quasars known reside at the limits of our observable universe's past, at a time when the first galaxies were forming. We see some quasars as they were when the universe was only 1 billion years old, or even less. There is a kind of poetry in that. These ancient light beacons have travelled across nearly the entire history of the cosmos to reach our telescopes. And they tell us that even in those early times, some black holes grew astonishingly massive. Indeed, one of the ongoing puzzles is how those black holes became so large so quickly to power quasars when the universe was still in its youth. It suggests that galaxy formation and black hole growth might have been more tumultuous and rapid than we once thought. Back when quasars were first discovered, scientists struggled to accept that a single object could produce so much energy. Many alternative theories were proposed: exotic stars, gravitationally contracting gas clouds, even hints of new physics. Slowly, the pieces fell into place. The spectral lines matched elements like hydrogen and magnesium, just redshifted to unexpected positions, confirming the immense distances. The variability of quasars, some flicker in brightness over months, hinted at a compact source, since a large galaxy-wide object couldn't change so quickly. All evidence pointed toward the notion of a supermassive black hole engine. This idea, once speculative, is now a central tenet of how we view galaxies. We believe most large galaxies have a monstrous black hole in their core, but only some, under the right conditions, blaze forth as quasars. The brilliance of quasars is not constant, and that adds to their intrigue. They can brighten or dim over time, suggesting that the amount of matter plunging into the black hole varies. Astronomers have watched quasars flare up as if they had sudden fuel infusions, then calm down again. These changes may happen over months or years, but they remind us that we are watching a dynamic process. A black hole, eating, burping, and perhaps pausing before its next feast. It's a window into the violent processes of galaxy centers. From an earthly perspective, quasars appear as tiny flickering points, often invisible except through powerful telescopes or on long photographic exposures. They don't look like the picturesque spiral or elliptical galaxies in astronomical images. Only by splitting their light or by detecting their powerful radio emissions do we recognize them for what they are. It is as if a single firefly on the horizon turned out to be a bonfire upon closer inspection, a bonfire shining across a continent. Having come to terms with quasars, astronomers eventually realized that these objects were part of a broader family of active galactic nuclei, where central black holes are gobbling up matter and producing prodigious energy. Quasars are one type, especially bright and often distant. But within this family, there was another, even more bewildering subgroup. Objects that seem to blaze even more unpredictably, as if the cosmic lighthouse's beam was pointed directly at us. These are the blazars, and they are, in a sense, quasars seen from a very specific vantage point. When the mighty engine at a galaxy's center directs its energy our way, the result is a cosmic jet screaming towards us, and the object transforms into one of the most violently variable light sources in the sky. Blazars are, in a sense, quasars seen head-on. If a quasar is like a cosmic lighthouse, a blazar is that lighthouse when you are standing directly in the path of its beam. In a blazar, a supermassive black hole is still at work, accreting matter and blasting out energy. But here, one of the twin jets of high-energy particles that shoot out from the polar regions of the black hole's accretion disk is aimed almost straight at Earth. This alignment makes all the difference. The already immense power of the quasar becomes even more concentrated and enhanced from our point of view. We essentially have a front-row seat to the show, and it is a wild one. Because we are looking nearly down the barrel of this cosmic jet, the light from a blazar is boosted by effects of relativity. The jet's particles are hurtling toward us at close to the speed of light, and as a result, their emissions are intensified and compressed in time. Changes that might be moderate in a more sedate galaxy appear extreme to us. A blazar can appear to erupt, flare, and subside on timescales of days or even hours. Imagine watching a distant beacon that unpredictably doubles in brightness overnight, then fades, then surges again with even greater intensity. For astronomers, tracking a blazar is both exciting and confounding. It's like observing a cosmic storm that changes form each time you glance at it. These objects earned their name from their blazing output. One of the first known blazars, a source called BL Lacertae, was originally misidentified as a variable star in our own galaxy because of how its brightness oscillated. Only later did scientists realize it was something far more distant and powerful. The core of a galaxy about 900 million light-years away, firing a jet almost directly at us. BL Lacertae became the namesake of an entire class of mysterious light variable sources. Today, when we say blazar, we mean any galaxy with a super bright, variable core powered by a black hole jet pointed toward Earth. They are among the brightest persistent objects in the observable universe across the electromagnetic spectrum, producing not just visible light and radio waves, but also X-rays and gamma rays. In fact, many of the high-energy gamma ray sources detected in the sky are blazars shouting across space with incredible luminosity. Standing on Earth, we are of course perfectly safe from these distant beacons. The energies may be huge at the source, but by the time their light and particles reach us, they are spread over astronomical distances. Yet, conceptually, to be in the sights of a blazar is a profound thing. It means we are aligned just so with a galaxy's central engine. Out of all the galaxies out there, only a tiny fraction have their jets pointing at us, which is why blazars are relatively rare. But those that do command attention, they serve as natural laboratories for extreme physics. The light from a blazar carries imprints of the processes near that black hole. Shock waves in jets, magnetic fields twisting and accelerating particles, perhaps even signals of how black holes launch these jets in the first place. Each sudden flare or dip in brightness is telling astronomers something about conditions millions or billions of light years away, in a place where matter orbits a black hole at nearly the speed of light. Blazars remain somewhat enigmatic. We have theories describing how they work, how the spinning black hole and its magnetic fields might fling out jets of plasma, and how looking straight into one of these jets makes it appear so bright. But there are details still not fully understood. For instance, why do some blazars have frequent outbursts while others stay relatively steady? What exactly triggers a flare? Is it a sudden gulp of new material by the black hole? Or collisions of shock waves within the jet? Or perhaps changes in the magnetic field configuration? Observing campaigns have caught blazars going through dramatic transformations. But connecting those observations to concrete causes is an ongoing challenge. They test the limits of our physics, pushing our models of particle acceleration and energy release to extremes. From a human perspective, there is something almost eerie about a blazar. Across incomprehensible distances, a galaxy's heart is effectively pointing at us, flashing and blazing as if trying to get our attention. Of course, it's not intentional, we just happen to be in the way of its beam. But it offers a reminder of how small we are in the grand scheme. Here we sit, watching light that has travelled for perhaps billions of years, telling a story about a turbulent cosmic engine that knows nothing of our existence. We happen to be aligned in just the right spot to witness its dance. As we marvel at the ferocity of blazars, we recognize that cosmic mysteries come in many forms. Our journey has carried us from fleeting radio flickers and singular signals to steady, distant glimmers of quasi-stellar beacons, and then to the roaring blaze of aligned galactic jets. Now our path turns closer to home, to the realm of stars that have died and yet still shine. Here we encounter pulsars, the spinning neutron stars, and focus on those that defy even the stringent rules we thought they followed. These tiny stellar remnants, no larger than a city, sometimes exhibit behavior so strange that it challenges our understanding of physics. In our own Milky Way galaxy, amid the spiral arms and nebulae, lie the cinders of long-dead stars that still pulse with a strange life. These are neutron stars, tiny, ultra-dense spheres left behind when massive stars explode. A neutron star spins rapidly, and if its magnetic field is angled just right, it emits beams of radio waves from its magnetic poles. As it spins, those beams sweep across space. To a distant listener with a radio telescope, the neutron star's emission can appear as a periodic blip of radio energy, a pulse that arrives with clockwork regularity. We call such an object a pulsar for its pulsating signal. It is essentially a stellar lighthouse, and most pulsars are remarkably steady, their pulses arriving on the dot, over and over, like the ticking of a perfect cosmic clock. The first pulsar was discovered in 1967, and its signals were so regular, about one pulse every 1.3 seconds, that the discovery team half-jokingly thought it might be a beacon from an intelligent civilization. They nicknamed it LGM-1 for Little Green Men, before more data revealed that it was not aliens at all, but an entirely new kind of astrophysical object. Since then, hundreds of pulsars have been found, each with its own rhythm. Some spin insanely fast, pulsing hundreds of times per second. These millisecond pulsars are like humming tops. Others rotate more slowly, perhaps once every few seconds. Usually, each is so consistent that you could set your watch by the beats. But as astronomers studied more of these cosmic clocks, they began to notice a few that behaved in perplexing ways, almost as if the clocks were occasionally breaking. One of the first odd behaviors observed was something called nulling. A pulsar would be merrily pulsing away, bleeps coming in steady succession, and then, without warning, the pulses would disappear. For a short time, or sometimes a very long time, the pulsar would fall completely silent, only to resume its regular ticking minutes, days, or even years later. Imagine sitting at a lighthouse and watching its beams sweep by again and again, then suddenly go dark for an unknown interval. And just when you've given up hope, the light blinks on, as if nothing happened. About 1 out of every 10 known pulsars exhibits some degree of this nulling behavior. For most, the silence might last only a few pulses. But a few extreme cases have stopped emitting for astonishing lengths, effectively hiding from detection. What causes nulling is still not fully understood. Perhaps the neutron star's magnetic engine falters temporarily, or its beam direction shifts out of view. One theory is that the mechanism generating the radio beam can occasionally shut off due to changes in the flow of charged particles in the star's magnetosphere. Whatever the cause, it's eerie to observe a usually reliable pulsar simply switch off, defying our expectations of constancy. Another unusual phenomenon is the pulsar glitch. Pulsars gradually slow down as they radiate energy, like a spinning top winding down over eons. But now and then, some pulsars abruptly speed up for a moment. It's as if our cosmic clock skips a beat, or rather, ticks a bit too quickly. These glitches are thought to be caused by events inside the neutron star. One idea is that the star's superdense interior, which may have a crust over a liquid core, occasionally readjusts itself. Picture the starquake of an object the size of a city, but containing more mass than the Sun. A slight crack or shift in the crust could make the pulsar's rotation suddenly jump. After the glitch, the star resumes its steady ticking at a slightly different rate. Glitches were a surprise when first observed, because they contradicted the expectation that these rotations should only ever slow down smoothly. Each glitch is a clue that inside these collapsed stars, there are exotic, fluid motions and stresses at play that we are only beginning to grasp. One of the most dramatic deviations ever seen happened in 2006 in a young pulsar located in the constellation of Aquila. This pulsar, normally a reliable emitter of pulses powered purely by its rotation, suddenly let loose a series of intense X-ray outbursts. Such behavior is typically seen only in magnetars, a rare type of neutron star with an extremely powerful magnetic field that can erupt with high-energy flares. For a rotation-powered pulsar to act this way was entirely unexpected. After the fireworks subsided, astronomers found that this pulsar's rotation had bizarrely altered. Its steady slowdown rate changed noticeably, as if the event had rearranged the star's internal dynamics. In essence, this pulsar briefly became something it was not supposed to be, blurring the line between categories of neutron stars. It left researchers puzzling over how a single incident could permanently change the behavior of a stellar remnant. The lesson was humbling. Even objects we think we have classified neatly can surprise us with a personality shift. And just when it seemed we had seen it all, along came pulsars that stretched the definition of what a pulsar can be. Traditionally, it was thought that if a neutron star rotated too slowly, it would no longer produce the radio pulses, falling below a so-called death line, where the mechanism fails. For decades, all known pulsars kept to relatively brisk tempos, at least one rotation every few seconds at minimum. But recently, astronomers stumbled on an object that flashes radio waves roughly once every 76 seconds. This ultra-slow pulse defied predictions, extending the pulsar family into regimes once thought impossible. Even more bizarre, a transient object was found that emits a burst of radio energy approximately every 18 minutes. It switches on for a few bright minutes, then disappears for a while, then returns again, following a cycle. Such a leisurely beacon is so far outside our expectations that, at first, researchers weren't sure what to call it. Is it a pulsar, a magnetar, or something entirely new? Whatever the classification, it demonstrated that nature's creativity can exceed the limits we imagine. In the quiet reaches of space, these little spinning beacons continue to astonish us. With each anomalous pulsar, we learn that our cosmic clocks can have quirks and hiccups. The fundamentals of pulsars remain: a rotating neutron star and its lighthouse beam. But the exceptions and oddities remind scientists that there is still much to learn about the extreme physics inside these stars. Perhaps future observations will unravel why some pulsars waver or erupt, while others keep perfect time. As our journey through these cosmic mysteries comes to a pause, we are left with a sense of wonder. We've listened to sudden radio bursts that leave us guessing, pondered a solitary signal that made us exclaim, "Wow!" Gazed at quasars and blazars blazing from unfathomable distances, and seen even the smallest stars bend the rules of nature. The universe is vast and full of questions, and each mystery we explored is a gentle reminder of how much we have yet to understand. For now, under the faint glow of countless stars, we let these cosmic enigmas rest in the silence of the night, awaiting that future day when curious minds and new instruments may finally decipher their secrets. In the silent depths of the cosmos, we drift onward, leaving behind familiar celestial sights. We venture now into a realm of cosmic giants, entire galaxies, each holding secrets that challenge our understanding. The darkness of intergalactic space is punctuated by the soft glow of distant galaxies. Yet some of those galaxies are not what they seem. Some are almost entirely invisible, hiding in plain sight, with hardly any starlight to announce their presence. Most galaxies shine with the collected light of billions of stars. But imagine a galaxy that contains almost no stars at all. Without the glitter of stars, such a galaxy would be essentially invisible, a vast mass drifting through space with hardly any light. Astronomers call these phantom islands in the cosmos dark galaxies, objects made of matter and gas, yet so barren of stars that they cannot be seen with ordinary telescopes. The idea of a dark galaxy is both simple and astonishing. We know that a galaxy's glow comes from its stars. Take the stars away, and a galaxy would be cloaked in darkness. For decades, scientists have theorized that such starless galaxies might lurk in the universe. Perhaps they form in regions rich in dark matter and gas, but never spark the birth of stars. If these dark galaxies exist, they could be numerous, hiding among the visible galaxies, like ghosts that only reveal themselves through subtle gravitational pulls or the faint radio whispers of hydrogen gas. It isn't as impossible as it sounds. In fact, astronomers already know that in ordinary galaxies, most of the mass is invisible dark matter. The bright stars and glowing gas are only a small fraction of what's really there. If dark matter outweighs normal matter by so much, it stands to reason that some clumps of dark matter could form galaxies without giving birth to many stars. In those hidden realms, dark matter's gravity would hold everything together, a ghost framework of a galaxy with only a trace of starlight, if any at all. Finding something that emits no light is a daunting challenge. Astronomers have turned to clever methods to hunt for dark galaxies. One way is to listen for the telltale signal of neutral hydrogen gas, a faint radio emission at a specific wavelength. Sensitive radio telescopes scan the sky for patches of hydrogen that have no stars visible. Another approach is to watch how galaxies move, searching for the gravitational tug of an unseen companion. If a luminous galaxy seems to dance around an invisible partner, that partner could be a dark galaxy exerting its pull from the shadows. Indeed, one of the ways astronomers have searched for dark galaxies is by conducting large sky surveys with radio telescopes. The Arecibo Observatory, for example, spent years scanning for neutral hydrogen signals floating in space without visible stars. These surveys turned up a number of mysterious gas clouds. Some of these clouds, found in various galaxy clusters and groups, have masses and motions suggesting they reside in dark matter halos. In other words, they behave like galaxies, but have little or no starlight. Each such discovery is a potential dark galaxy candidate, though confirming their nature is challenging. Astronomers must rule out the possibility that these are just gas stripped from known galaxies, which often mimics the same signals. There have been tantalizing hints of these invisible galaxies. In the mid-2000s, astronomers studying the Virgo cluster, a large gathering of galaxies, detected an odd cloud of hydrogen. This cloud, catalogued as Virgo 21, had no stars that anyone could see. Yet it was exerting a mysterious gravitational pull on a nearby spiral galaxy. It was as though an invisible mass was lurking in the cluster. For years, researchers puzzled over this mysterious object. Some concluded that Virgo 21 was in fact a dark galaxy, a body made mostly of dark matter and gas, with virtually no starlight of its own. Others suspected it might just be debris, the cast-off gas from a past galactic collision. The debate itself was revealing, showing how hard it is to pin down a truly starless galaxy. But the possibility hung in the air that somewhere out there, real dark galaxies were waiting to be found. Then came a discovery that electrified the astronomical community. In 2016, scientists unveiled a galaxy that seemed to be almost entirely made of darkness. They named it Dragonfly 44. This faint smudge in the Coma cluster turned out to have a mass comparable to our Milky Way, but with less than 1% of the stars. Imagine a galaxy as massive as a giant, yet so dim that only a handful of stars twinkle within it. Observations suggested that about 99.99% of Dragonfly 44's mass is invisible dark matter. It was as though an enormous city had only a few streetlights glowing. All the structure and mass were there, but cloaked in an almost complete night. Dragonfly 44 gave astronomers a glimpse of what a dark galaxy might look like if it had at least a sprinkling of stars to betray it. It appears as a hazy, diffuse object, barely noticeable against the blackness of space. Before this, such ultra-diffuse galaxies were largely theoretical. Now here was one with the heft of a major galaxy, but virtually none of the usual gleam. The discovery raised profound questions. How could such a massive galaxy form without lighting up with stars? How many more like it could be hiding in the vast cosmic dark? Dragonfly 44 turned out not to be alone. As astronomers began looking, especially in clusters of galaxies, they found dozens of these ultra-diffuse galaxies, large in size but faint in light. Some, like Dragonfly 44, appear heavily dominated by dark matter. Most ultra-diffuse galaxies do contain at least some stars, but their surfaces are so dim that they verge on invisibility. They populate places like the Coma cluster by the hundreds, hiding in plain sight until special techniques revealed their ghostly glow. Their existence hints that the universe contains a whole menagerie of barely visible galaxies, bridging the gap between normal galaxies and the completely dark ones scientists envision. The origin of these dark galaxies remains uncertain. One idea is that they are failed galaxies, clumps of matter that gathered enough mass to form a galaxy, but somehow never ignited many stars. Perhaps long ago, these clouds of gas were flooded with energy by violent events, preventing stars from taking shape. Another possibility is that they formed in isolation, quietly collecting dark matter and gas, but lacking the density triggers needed for starbirth. Intriguingly, some scientists suspect that dark galaxies were the stepping stones that built larger galaxies. In this view, our own Milky Way could have grown by swallowing many small dark galaxies, unseen mergers that added their mass and gas. These hidden contributors would have fueled star formation in the larger galaxies without ever shining on their own. If so, dark galaxies might have played a crucial role in growing the bright galaxies we know, quietly shaping the cosmos from the shadows. To this day, no completely starless galaxy has been definitively confirmed. Almost every time we find a candidate, a few faint stars or alternative explanations emerge under closer examination. Dark galaxies, if they exist, are elusive quarry. They might populate the cosmos in great numbers, especially as small satellites around bigger galaxies, yet be practically invisible. It is a cosmic irony that the universe could be teeming with galaxies we cannot see, each one a heavy shadow playing gravitational tricks on the visible world. These invisible galactic islands remind us of how much is still hidden in the cosmic ocean. Future discoveries may come from clever, indirect observation. For instance, a completely dark galaxy might betray itself through gravitational lensing, the way its gravity bends the light of more distant objects. If astronomers notice a patch of sky where background galaxies appear oddly distorted, like light passing through an invisible lens, they might have found a dark mass drifting there. In a universe filled with hidden matter, such gravitational sleuthing could one day uncover a galaxy made of darkness. The thought of finding a galaxy by its shadowy gravitational imprint alone is both strange and exciting. There have also been curious cases that tantalized researchers. At one point, the Hubble Space Telescope observed a bright quasar, a luminous beacon powered by a supermassive black hole that appeared to float in space with no surrounding galaxy. Quasars normally live in the centers of galaxies, so this was puzzling. Some experts speculated the quasar might inhabit a dark galaxy, shining alone while its host galaxy remained invisible. Later analyses did find a faint smattering of stars around the quasar, suggesting a very dim galaxy was there after all. Even so, the brief prospect of a quasar inside a dark galaxy fired imaginations, showing how we're just beginning to probe these hidden corners of the cosmos. If dark galaxies do exist in large numbers, it means that the grand architecture of the universe might be even more intricate than the light we see indicates. We often picture the cosmos as a tapestry of shining galaxies, but there could be a hidden tapestry woven from dark matter and gas alone. The thought that entire galaxies might float through space unseen challenges us as observers. What else are we missing? It also inspires a sense of wonder that even in the vast darkness, structures and systems can take shape and persist quietly. Dark galaxies, whether ultimately confirmed or not, remind us that the universe does not always present its treasures openly. Some remain in shadow, waiting for curious minds to tease them out of the darkness. The concept of dark galaxies stretches our imagination. It beckons us to consider the possibility of entire galaxies as dark, silent silhouettes drifting among the stars. As we ponder these unseen giants, the universe offers other enigmas in the realm of galaxies. Not all galactic mysteries are hidden in darkness. Some shine in unusual shapes that challenge our understanding. Even among the galaxies we can see, a few are so strangely formed that they too seem to defy explanation. We encounter galaxies that have reshaped themselves into cosmic rings, as if displaying the aftermath of extraordinary events. High above the galactic plane, imagine beholding a galaxy unlike any other. Instead of the familiar spiral arms or amorphous glow, you see a luminous ring floating in space. A circle of sparkling blue stars wraps around an eerily empty center, as if a cosmic wheel were left spinning in the void. In the middle of that ring lies a small ball of older, reddish stars, a core, separated from the outer ring by a gap of darkness. The sight is mesmerizing and strange. A galaxy turned into a celestial ring, beautiful and utterly rare. The visual allure of a ring galaxy is undeniable. Some astronomers have poetically compared them to cosmic rose windows or celestial donuts suspended in space. To the human eye, through a powerful telescope, a ring galaxy can look like a delicate circular wreath made of stars. In photographs, the contrast of the colourful ring against the blackness of space and the faint glow of the central core is striking. It is a reminder that the cosmos often produces structures that can be both scientifically intriguing and aesthetically breathtaking. These galaxies are as much works of cosmic art as they are subjects of astrophysical research. Ring galaxies, as astronomers call them, are some of the rarest galaxies known. Out of tens of thousands of galaxies we observe, only a handful take on this striking ring shape. The first and most famous example was discovered in 1950 and is known as Hoag's object. At first glance, Hoag's object looks like a perfect circle of stars encircling a lone sphere of light at the center, with nothing but emptiness in between. This peculiar structure baffled scientists for decades. How could a galaxy form such a detached ring of stars, with a barren gap separating the ring from its core? For a long while, Hoag's object stood nearly alone, as an oddball of the cosmos. Decades passed before other ring galaxies were identified, which slowly revealed that Hoag's was not an isolated fluke, but part of a small family of ringed wonders. Each new discovery, some rings off-center or slightly distorted, added pieces to the puzzle. With more examples to study, astronomers gained confidence in forming theories for how these stellar rings came to be. It was as if nature had left clues scattered across the sky, each ring galaxy another snapshot of an ongoing story. When Arthur Hoag first spotted his now famous object in 1950, even classifying what he was seeing was difficult. Here was something that looked like a ring-shaped nebula at first glance. But unlike any planetary nebula or supernova remnant known, as telescopes improved, it became clear this ring was enormous and far away. Not a nearby cloud, but a galaxy-sized system. For years, Hoag's object defied classification, sitting oddly in catalogues as a peculiar galaxy. It wasn't until more ring galaxies were identified later in the century that astronomers realized Hoag's object was the prototype of a whole new category. That initial confusion reflects just how strange this formation appeared when it was alone in its class. Early on, some wondered if the ring might be an illusion, perhaps the light of a distant galaxy distorted into a ring by a gravitational lens in front of it. But careful observations showed that the ring and the central core share the same distance and velocity. They truly belong to one unique galaxy. Others proposed exotic scenarios. Maybe a turbulent galactic disk somehow threw out a ring of stars, or two galaxies merged in an unusual way. Yet these ideas struggled to explain all the details. The mystery of Hoag's object persisted, a cosmic puzzle suspended in space. In the traditional classification of galaxies, the famous Hubble tuning fork, there is no category for ring galaxies. They were so uncommon that early astronomers like Edwin Hubble did not include them in the usual spiral, elliptical, or irregular classes. Ring galaxies are truly outliers. Their existence expands our notion of what a galaxy can look like. They also illustrate that the cosmic stories of galaxies can sometimes take unusual turns, producing structures that don't fit neatly into any category. Much like finding a square peg in a round hole, the ring galaxy challenges our attempts to neatly organize the universe's diversity. Almost every galaxy can be classified as a spiral, elliptical, or irregular shape, but ring galaxies make up only a tiny fraction. Astronomers estimate that only roughly 1 in every tens of thousands of galaxies is a ring galaxy. We have identified only a relatively small number of them across the sky. Each discovery of a new ring galaxy is met with interest, as it provides another example to compare and study. Every ring has its own subtleties. Some have slight twists, others have bright clumps along the ring indicating clusters of newborn stars, and a few even have more than one ring concentric with each other. These nuances give researchers clues about the timing and dynamics of the collisions that formed them. In this way, each ring galaxy is like a cosmic laboratory, teaching us how galaxies react to gravitational disturbances. Over time, more ring galaxies were found, and with them came clues that helped unravel the mystery. Astronomers noticed that many ring galaxies have telltale signs of cosmic violence. The outer rings are filled with young blue stars, while the cores consist of older, redder stars. This contrast hints at a dramatic event that sparked new star birth in a ring around an older galaxy. The leading theory that emerged was a cosmic collision, almost like a bullseye shot. Imagine a smaller galaxy plunging directly through the heart of a larger spiral galaxy. In that moment, spanning perhaps tens of millions of years in slow motion, the gravitational shock of the intruder sends a ripple across the larger galaxy's disk. Like a stone dropped into a pond, that ripple pushes gas and dust outward into a widening ring. The expanding wave compresses the gas in its path, triggering it to collapse and form new stars. A brilliant circle of hot, young stars emerges, spreading outward from the galaxy's center. The intruder galaxy itself may continue on its way, or eventually merge and disappear, but it leaves behind the ring as a lingering echo of their collision. To test these ideas, scientists have turned to computer simulations. By inputting the laws of gravity and the properties of galaxies, they can crash virtual galaxies together and watch the outcome. Through such simulations, a satisfying picture emerged. When a small galaxy plunges through a larger one, a ring does indeed form under the right conditions. The simulated ring galaxies closely resemble real ones, complete with central cores and expanding rings of stars. These cosmic experiments have strengthened the case that ring galaxies are born from chance alignments and collisions, giving scientists confidence that they understand the general mechanism. Yet, even with simulations, the sheer beauty and symmetry of objects like Hoag's object feel almost coincidental, a perfect cosmic timing that we were fortunate to witness. Not all ring galaxies are as perfect and symmetric as Hoag's object. Some appear more elliptical or lopsided, their rings off-center or uneven. This can happen if the collision that formed the ring was not a direct head-on strike, but a bit off to the side. In other cases, we might be seeing a circular feature at an angle, which makes it look stretched into an oval. Even in their imperfections, these rings still captivate astronomers. They demonstrate that nature can create many variations on the ring-making process, depending on the angles and timing of galactic encounters. One spectacular ring galaxy, known as the Cartwheel Galaxy, offers a glimpse into such a cosmic aftermath. The Cartwheel was likely a normal spiral galaxy until a smaller galaxy barreled through it some 300 million years ago. Now it looks exactly like its namesake, a giant wheel in space with a bright ring measuring over 100,000 light-years across. The collision lit up the ring with intense star formation, creating clusters of massive, hot stars that glow blue and ultraviolet. Even long after the impact, the ring continues to expand outward. In time, it may slow and fade, but for now, the Cartwheel remains a shining example of a galactic ring forged by a violent encounter. Sometimes the culprit responsible for a ring galaxy can still be seen nearby. In the case of the Cartwheel Galaxy, for instance, there are smaller companion galaxies in its vicinity. One of those is likely the intruder that ploughed through the Cartwheel's disk, triggering the spectacular ring. In other ring galaxies, the absence of a visible companion suggests the intruder may have merged or moved on long ago. Identifying the former companion can solidify the collision theory for a given ring galaxy. It's a bit like finding the stone that caused ripples in a pond. If you spot the stone at rest on the pond's edge, it confirms how the ripple was made. Still, not every ring galaxy comes with an obvious culprit. Hoag's object remains enigmatic. No trace of a second galaxy is seen near it, leaving its past a subject of speculation. Perhaps the intruder that created Hoag's ring merged into the core and is now unrecognizable, or maybe some other more unusual process crafted its perfect ring. Whatever the cause, Hoag's object stands alone in space, serene and puzzling, a reminder that some galactic secrets take a long time to unravel. In the grand scheme of time, a ring galaxy is likely a temporary phase. The ring of stars will eventually disperse or blend back into its surroundings as the gravitational dances continue. The brilliant young stars in the ring will burn out over millions of years, and without new gas to sustain the ring, it could dissipate into a more ordinary distribution of stars. What remains might be an enlarged, perhaps more diffuse galaxy that bears only subtle scars of its ringed past. Knowing this, seeing a ring galaxy is like catching a cosmic event in mid-performance, a rare snapshot of a galaxy in transformation. If one could journey through a ring galaxy, the experience would underscore its odd structure. Imagine starting at the galaxy's center, in the region of the old yellow stars. As you travel outward, you would leave the glow of the central core and enter a vast darkness. For many thousands of light years, there might be almost nothing, a startling empty gulf where few stars reside. Then, suddenly, you would emerge into the brilliance of the ring itself. Here you'd find countless hot blue stars lighting up the surrounding space. It would be a dramatic transition from void to vibrance, as if crossing from a dark, empty desert into a bustling, youthful city of stars. Such a journey through the gap truly highlights how peculiar a ring galaxy's layout is. These celestial rings are a testament to the dramatic interactions that galaxies can undergo. They challenge our classifications and show that even galaxies can wear uncommon shapes for a time. From nearly invisible dark galaxies to radiant ring galaxies, the cosmos continually surprises us with its variety. Yet, not all mysteries are about unusual appearances. Some are about things expected but not seen. One perplexing cosmic riddle lies not in what galaxies show us, but in what seems to be missing around them. It's the curious case of the galactic companions we expected but cannot find. Galaxies are not solitary wanderers. They often come with an entourage of smaller companions. Our own Milky Way, for instance, is orbited by several dwarf galaxies. The two most prominent, known as the Magellanic Clouds, are visible as hazy patches in the southern sky. Beyond those, astronomers have found a collection of even tinier galaxies swarming around us, faint and diminutive satellites that cling to the Milky Way's edges. And yet, a puzzling question arose. Were there too few of these companions? When scientists simulated the growth of galaxies in a universe dominated by dark matter, they encountered a striking prediction. The models showed that a galaxy the size of the Milky Way should be surrounded by hundreds of smaller dark matter clumps, potential dwarf galaxies in the making. These simulations produced a veritable swarm of satellites. But when astronomers looked at the actual sky, they did not see hundreds of dwarf galaxies orbiting the Milky Way or other similar galaxies. At best, only a few dozen had been spotted, and for years, only a dozen were known around the Milky Way. There was a glaring discrepancy between theory and observation. This became known as the missing satellite problem. To put it in perspective, imagine overlaying two pictures of our galactic neighborhood. In one picture, the theoretical one, the Milky Way is circled by a swarm of dark halos, each a potential tiny galaxy, like hundreds of fireflies around a great lantern. In the other picture, the observed one, only a few of those fireflies shine visibly. The rest are dark, invisible to our eyes and instruments. This stark contrast between the expected swarm and the observed handful is at the heart of the mystery. Simply put, the missing satellite problem is the question of why we don't observe as many small galaxies as our theories say should exist. It's as if a crowd was expected around every giant galaxy, but only a handful showed up. For the Milky Way, the known satellite galaxies could be counted on one's fingers for a long time. Where were the others? Had we missed them, or did they never form at all? This cosmic mystery suggests that either our universe is hiding these little galaxies from us, or our understanding of how galaxies form needs revision. The discrepancy became widely discussed around the turn of the 21st century, when high-resolution simulations first laid out their predictions. Researchers like Anatoly Klipin and Ben Moore published results starkly showing that a Milky Way-sized halo should host dozens, even hundreds, of subhalos massive enough to be galaxies. At that time, only around 11 satellite galaxies had been documented around the Milky Way. The contrast was startling. As one scientist quipped, it was like expecting a swarm of bees, but only finding a few droning around. Clearly something was off. The missing satellites had to be hiding or never formed, and either possibility was intriguing. Astronomers began to brainstorm explanations. One possibility was that the missing satellites were actually there, but incredibly hard to spot. Perhaps most of the predicted dwarf galaxies were extremely faint, with only a few old stars left, making them nearly invisible against the dark sky. Over the last 2 decades, improved telescopes have indeed uncovered many ultra-faint dwarf galaxies around the Milky Way, little smudges of stars so dim that they were previously overlooked. Every new discovery adds a piece to the puzzle, but even these do not fully account for the hundreds of satellites that simulations predict. There still appear to be far fewer luminous satellites than theory suggests. As sky surveys improved, especially in the 2000s and 2010s, astronomers began to unearth a multitude of previously unknown dwarf galaxies. These newly found satellites were much fainter and smaller than the ones discovered in earlier decades. Some contained mere thousands of stars, so few that they resembled star clusters more than typical galaxies. Yet their stars' motions indicated the presence of dark matter, confirming them as true galaxies, just extremely feeble ones. One by one, the the count of Milky Way companions climbed into the dozens. This partly closed the gap in numbers, suggesting that the cosmos had indeed been hiding many of its smallest galaxies just beyond our detection limits. However, even with these ultra-faint galaxies tallied, a sizable gap remained. In fact, some of the tiniest galaxies ever discovered have been eye-opening in their own right. For example, one ultra-faint dwarf galaxy was found to have only a few hundred stars. To put that in perspective, a typical globular cluster can have tens of thousands of stars, and our Milky Way has hundreds of billions. That diminutive galaxy is barely glowing at all, yet it is held together by a substantial amount of dark matter. Such finds emphasize that galaxies can exist on the brink of invisibility, and there could be many more of them lurking around us, only detectable through painstaking searches. Another idea looks back to the early universe, when these small galaxies were just forming. In those primordial times, intense radiation flooded space as the first stars and galaxies lit up. That radiation could have heated and stripped away the gas from smaller fledgling galaxies, preventing them from ever forming many stars. If a tiny dark matter halo lost its gas early on, it would remain a mostly dark clump, essentially an invisible galaxy with no stars to shine. In this scenario, the satellites are indeed out there, but they are dark. Essentially, the dark galaxies we imagined earlier. They would be orbiting their parent galaxies as unseen halos of matter, ghosts that are felt through gravity, but never directly observed. Could it be that some satellites did form, but were later destroyed? This is another angle to the missing satellite problem. Over billions of years, the Milky Way has likely merged with and absorbed some of its smaller companions. When a dwarf galaxy is torn apart by our galaxy's tides, its stars disperse. We might no longer count it as a distinct satellite, but its remnants are still around us as diffuse stellar streams. In that sense, a part of the missing satellites might not be missing at all. They were simply eaten by their larger neighbour. The evidence of those past meals is subtle, but as we've seen, it can be detected in the Milky Way's halo as ghostly streams of stars. It's also possible that our theory needs adjusting. The simulations that predict hundreds of satellites assume a particular nature for dark matter, that it is cold and forms lots of small clumps. If, however, dark matter behaves slightly differently, the number of small halos could be fewer. Some researchers have suggested that if dark matter particles move faster or interact in subtle ways, they might not form so many tiny satellites to begin with. In that case, the missing satellite problem might not be a problem at all, but rather a sign that our dark matter model needs fine-tuning. For now, the mystery remains only partly resolved. On one hand, we have indeed found more dwarf galaxies in recent years, suggesting that some of the gap was simply our lack of detection. On the other hand, even with these additions, there are still far fewer satellites than naive models predicted. The most massive predicted satellites in simulations don't quite match the ones we see, hinting that something interesting is going on. It might be that the universe formed many dark satellites that we'll never see, or that the conditions for making a visible galaxy are stricter than we thought. Either way, the missing satellite problem has been a humbling reminder that even our best theories can miss important details. This situation has led astronomers to give that aspect a nickname: the too big to fail problem. In essence, the simulations predict some dark matter clumps so large that they should have easily formed stars. They were too massive to remain totally dark. Yet we do not see galaxies corresponding to all of those big subhalos. Those massive subhalos would presumably have been too hefty to avoid making at least some stars, so their absence is striking. Solving this piece of the puzzle might require refining our understanding of dark matter itself, or finding a few more elusive mid-sized dwarfs that have so far escaped detection. This discrepancy has even led some to question our theories of gravity. If there were no dark satellites at all, could it be that our simulations, using Newtonian gravity and dark matter, are oversimplified? A few researchers proposed that perhaps the force of gravity works differently on small scales, which might naturally produce fewer satellites. However, most evidence still points toward the existence of dark matter and the likelihood that many satellites are simply hard to see. The consensus leans toward astrophysical solutions, like those faint galaxies or feedback processes, rather than new physics. Still, the discussion illustrates how puzzling this problem was. It forced scientists to re-examine fundamentals and consider all possibilities. And it's not just the Milky Way. Other large galaxies like Andromeda also show a similar dearth of satellite galaxies when compared to simulations. Across the universe, whenever we peek at galaxy systems, we wonder what we might be missing. This hints that the missing satellite issue is a general feature of galaxy formation, not just a fluke of our home in the universe. It adds weight to the idea that either a lot of small galaxies are dark and hard to find, or our models need some adjustment on small scales. Either way, cosmologists take this puzzle seriously, because solving it teaches us about the nature of dark matter and the history of how galaxies assemble. This conundrum of unseen galaxies highlights how much is left to learn. While we ponder the absence of expected galaxies, we can clearly witness another aspect of galactic life: interaction. Galaxies that are present sometimes meet in dramatic fashion. In contrast to the quiet missing companions, there are galaxies that crash together in colossal mergers. Our journey now turns to those grand cosmic encounters, where entire galaxies collide and coalesce, reshaping the heavens in slow-motion grandeur. In the quiet of space, galaxies sometimes drift into each other's embrace. It might seem impossible, given the immense distances between stars, but gravity has a way of bringing these stellar cities together. Over billions of years, galaxies that draw near can merge in a slow, magnificent collision. Picture two swirling galaxies beginning to overlap. Their stars, planets, and clouds of gas intermix under the tug of gravity. What follows is not a sudden crash, but a drawn-out dance, a gravitational ballet that unfolds over a very long time, transforming both partners in the process. If we imagine the future, our own galaxy is destined for such an encounter. The Milky Way and the Andromeda galaxy are on a slow collision course. Though separated by vast space now, gravity is drawing them inexorably together. Far in the future, an observer in the Milky Way would see Andromeda as a faint blur that grows larger with each eon. Over millions of years, that hazy patch will expand into a spectacular view, eventually dominating the night sky. Generation after generation might witness Andromeda's gentle approach until, at last, the two galaxies begin to overlap. Future skies will be filled with the combined glow of billions of stars from both galaxies as they commence their cosmic dance. It will be a sight both marvelous and melancholy, the merging of two stellar kingdoms into one. When galaxies collide, individual stars almost never slam directly into one another. The spaces between stars are so vast that two galaxies can interpenetrate like ghosts. However, the gravitational forces during the encounter wreak havoc on galactic structure. As the galaxies pass through each other, their shapes distort dramatically. Tidal forces stretch out long streamers of stars and gas from each galaxy, casting material into space. These tidal tails can arc far out into the intergalactic void, luminous tracers of the encounter. Imagine enormous tendrils of stars being drawn out, as if the galaxies were pulling each other apart. A real-life example of this cosmic demolition is unfolding in a pair of merging galaxies, known as the antennae. They are nicknamed for the two long arcing star streams that extend outward from the galactic cores, resembling the antennae of an insect. These streams are composed of stars flung far into space by the interaction. The two galaxies' cores are entwined in a chaotic embrace, enshrouded in turbulent clouds of gas and dust. Within those clouds, a frenzy of star formation is taking place, vast clusters of new stars igniting as the colliding galaxies compress the gas. The antennae galaxies give us a snapshot of a merger in progress. We see not only the impressive tidal tails, but also the glowing regions of newly born stars triggered by the collision. Such interactions often ignite a brilliant burst of star formation. As gas clouds in the colliding galaxies crash together or get compressed, they can trigger a frenzy of new stars being born. In the midst of chaos, regions light up with hot young stars and glowing nebulae. Two merging spirals might briefly become a spectacular starburst galaxy, shining more brightly as they form stars at a feverish rate. It is as though the collision breathes new life into them before they settle down. Over millions of years, this fireworks show gradually subsides as the gas is used up or dispersed. At the heart of colliding galaxies, another drama can unfold. As the galaxies merge, their central supermassive black holes may eventually find each other and spiral together. Before they coalesce, each black hole can gobble up the sudden influx of gas funneled towards the center during the merger. This process can ignite a quasar, a fiercely bright beacon powered by accretion onto the black hole. For a time, the merging galaxy's core can outshine the entire galaxy, blasting out energy. Eventually, the two black holes might even merge into a single, larger black hole, sending ripples through spacetime known as gravitational waves. These hidden finales of galaxy collisions add another layer of excitement to an already grand event. As the dance continues, the two galaxies loop around each other, drawn back together by their mutual gravity. Each pass strips away more of their original structure. Spiral arms get tangled and lost, star orbits are scrambled, and any distinct disk may puff up. Eventually, the galaxies coalesce into one. The end result of a major merger is often an entirely new galaxy, typically more spherical or elliptical in shape. Where once two graceful spirals wandered, now a single, larger galaxy remains, its form more rounded, and its past spiral patterns erased by the violence of union. The aftermath of a major merger leaves a galaxy changed in fundamental ways. The once distinct rotating disks of spiral arms are gone, replaced by a more amorphous spread of stars. Much of the gas will have been either converted into new stars or heated and expelled. With little fuel left for further star birth, the merged galaxy tends to enter a quieter phase. Astronomers see this in the population of stars. They become predominantly older, reddish stars. The youthful blue hue of active star-forming regions fades away. The new galaxy is often an elliptical, lacking the orderly structure of a spiral, and it can shine as a giant ellipsoidal ball of aging stars, a red and dead galaxy, as astronomers sometimes say. Yet even in this calmer state, The galaxy is now the product of all that came before, a monument to the union of two star systems that once were separate. Many of the giant elliptical galaxies we observe in the universe are thought to be the aftermath of such collisions. Over cosmic time, galaxies grow by merging. A large galaxy like the one at the center of a cluster may have absorbed dozens of smaller ones. Every big galaxy's history is a tale of past collisions and cannibalism. Even our Milky Way carries evidence of past mergers in the form of those faint tidal streams of stars in its halo. It has dined on smaller galaxies in the past, and it will do so again in the future. Collisions can come in all scales. While two giant galaxies merging is the most spectacular, even small galaxies can collide and merge. Dwarf galaxies frequently fall into larger ones or bump into each other. In galaxy groups, multiple small interactions might be happening simultaneously. There are instances of 3 or more galaxies all merging together in a cosmic pileup, creating chaotic structures. In rich clusters of galaxies, the central dominant galaxies often grow huge by assimilating others over time. Thus, collisions are not an occasional curiosity, they are a key part of how galaxies evolve. We live in a universe where even these colossal structures routinely recycle and reinvent themselves by merging. Over billions of years, repeated collisions can produce truly colossal galaxies. In the dense environments of galaxy clusters, the largest galaxies, often sitting at the center, are thought to be the product of many mergers piled on top of one another. They sprawl with trillions of stars, a diffuse megagalaxy formed from the cannibalization of countless smaller ones. One example is the giant elliptical galaxy at the heart of the Virgo cluster, which outshines our Milky Way many times over. It's a melting pot of the cluster's former members. These behemoths are cosmic testaments to the cumulative power of collisions, showing that even the mightiest galaxies are built by continual acts of cosmic combining. Not every galactic encounter ends in a complete merger. Sometimes galaxies just have close encounters, flybys that dramatically influence them, but eventually leave them separate. Even a glancing pass can twist spiral arms or spark bursts of star formation. A classic example is the Whirlpool galaxy, M51, and its smaller companion. The companion galaxy's near collision with the Whirlpool is what likely gave M51 its grand, sweeping spiral structure and triggered bright star-forming regions in its disk. After their encounter, the two galaxies did not immediately merge, but the gravitational disturbance was enough to transform the Whirlpool into one of the most picturesque spirals in the sky. Thus, cosmic interactions come in many degrees, from gentle brushes to head-on collisions, each contributing to the evolving artwork of the universe. In the chaotic gravitational dance of a collision, some stars can even be completely thrown free of both galaxies. These rogue stars end up wandering in intergalactic space, perhaps carrying any orbiting planets with them into the lonely void. While rare on a percentage basis, these ejections are yet another consequence of the tremendous gravitational forces at play when galaxies interact. Galaxy collisions are a reminder that the universe is dynamic and ever-changing, even on the grandest scales. What looks serene and eternal in the sky is in fact constantly evolving. Two galaxies can fall together and become one, altering the cosmic landscape over time. In the aftermath, new stars and structures emerge, while some chaos gradually settles into order again. It is a slow cosmic renewal. Galaxies can be seen as cosmic living entities that grow by consuming others. If we could watch the universe in fast forward, we'd witness a grand ballet of galaxies assembling, smaller proto-galaxies merging into bigger ones, groups of galaxies coalescing into fewer, larger members, The night sky of the distant future will look very different from today's, in part because of these majestic collisions and fusions. Our journey through cosmic phenomena continues, as we turn now to the delicate remnants these collisions often leave behind, the ethereal streams of stars that are the ghosts of galaxies past. All around the Milky Way and other galaxies, there are pale, wispy structures that only the keenest observations can reveal. These are ghostly streams of stars, so faint that they blend into the darkness of space. They drape around galaxies like gossamer threads, remnants of something that has been torn apart. At first glance, they might go unnoticed, but with long exposure images and careful mapping, they appear as subtle, elongated clouds of starlight, arcing around a galaxy's halo. These are the leftovers of cosmic meals, the faint traces of smaller star systems that have been pulled apart by tidal forces. When a dwarf galaxy or a star cluster ventures too close to a much larger galaxy, the difference in gravity across it can rip it asunder. The smaller system's stars are drawn out, strung along the larger galaxy's gravitational field. Over time, the stars that once were bound in a tight group become a long, thin stream orbiting the big galaxy. These tidal streams, as astronomers call them, are essentially the stretched remains of the unfortunate smaller galaxy or cluster. What's left is not a cohesive galaxy anymore, but a river of stars coursing through space, slowly dispersing as it goes. The discovery of stellar streams is a relatively recent chapter in astronomy. In the 1990s, astronomers first detected a gigantic stream of stars looping around the Milky Way, the remains of the Sagittarius dwarf galaxy. It was a revelation, showing clearly that our galaxy was in the process of tearing a smaller galaxy apart. In the years that followed, more streams were found. Some were identified in surveys, like the Sloan Digital Sky Survey, where maps of millions of stars revealed coherent structures. By mapping the positions and motions of these stars, scientists could delineate the path of each stream, like following a trail of breadcrumbs. Each new stream discovery confirmed that the Milky Way has been feasting on smaller systems throughout its history. Our own Milky Way is quietly weaving such ghostly tapestries even now. One of the most famous streams comes from the Sagittarius dwarf galaxy, a small neighbour that our Milky Way has been gradually dismantling for billions of years. The stars of Sagittarius have been torn out and now wrap around our galaxy in a huge loop. Astronomers have mapped this stream as it flows over the poles of the Milky Way and back around, like a stellar halo within a halo. To an observer, the individual stars in the stream are almost indistinguishable from regular stars in the sky. But when plotted out, they form a coherent band, the imprint of a galaxy being digested by our own. The Milky Way has multiple such streams meandering through its outskirts. Dozens of them have been found, each telling a story of a past encounter. Some streams originate from other dwarf galaxies, while others are the remnants of globular clusters that strayed too close and were shredded. For instance, a globular cluster named Palomar 5 has left behind a remarkably thin stream of stars, like a strand unravelling from a cosmic tapestry. Every stream is a clue, a piece of evidence of something that once was whole and now persists only as a line of stars drifting in the galactic halo. Not only stars, but gas too, can form ghostly streams. The Magellanic Clouds, two dwarf companions of the Milky Way, are trailed by an immense stream of hydrogen gas, aptly named the Magellanic Stream. It stretches over half the sky. For a long time, this stream appeared to contain no stars, only gas torn from the Magellanic Clouds by gravitational interactions. Recently, however, astronomers identified a few stars within the Magellanic Stream as well, indicating that even this gaseous streamer carries some stellar passengers. This discovery blurs the line between pure gas streams and stellar streams, and underscores how thoroughly galaxies can be stripped of both stars and gas when they interact. A game-changer in stream detection has been the European Gaia spacecraft. Launched in 2013, Gaia has measured the precise positions and movements of over 1 billion stars in our galaxy. With this wealth of data, astronomers can find groups of stars traveling together through space, the signature of tidal streams. Gaia's observations have unveiled several previously unknown streams, including some that were invisible against the crowded background of the Milky Way until their motions were analysed. It's as if Gaia gave us X-ray vision to see the skeletal outlines of past mergers in our galaxy's halo. Thanks to such missions, the once hidden patterns of star debris are coming into focus, enriching our understanding of the Milky Way's growth. One striking feature in the Milky Way is the so-called Monoceros ring, a large, low-density ring of stars wrapping around the galaxy's outer disk. It was discovered in the early 2000s and is believed to be the tidal debris of a dwarf galaxy that crashed through the Milky Way's disk long ago. This finding was astonishing because it suggested that even the flat disk of our galaxy has assimilated smaller galaxies, leaving ripples and loops of stars as evidence. The Monoceros ring lies along the plane of the Milky Way, different from the polar-oriented Sagittarius stream, showing that galactic cannibalism can occur at various angles and produce different patterns of debris. Other galaxies, too, reveal these ethereal structures when we look carefully. The Andromeda Galaxy, our nearest large neighbour, is enveloped by sprawling streams from past mergers. One giant loop of stars in Andromeda's halo stands out as the remnants of a galaxy it devoured long ago. In recent years, deep surveys of the skies have started to uncover faint streams around numerous galaxies. It appears that almost every large galaxy has some ghostly stream if you can detect it, a testament to the universality of galactic cannibalism. Galaxies grow by consuming others, and these streams are the fading scars of those acts. As we look beyond our own galaxy, we find that stellar streams are not unique to the Milky Way or Andromeda. Even relatively distant galaxies, when imaged deeply, reveal faint streamers. One famous case is a spiral galaxy catalogued as NGC 5907. In long-exposure photographs, it shows an enormous loop and whirls of stars surrounding it, likely the remnants of a satellite galaxy it devoured. What makes this case special is that amateur astronomers using modest telescopes and great patience were the first to uncover those ghostly loops. It's a reminder that there are secrets in the sky, subtle enough to hide from quick glances, yet available to those who look long and carefully. All around, in various galaxies, we catch hints of ethereal tides of stars, marking where cosmic meals took place. These streams are not just beautiful, they are also scientifically useful. Because the stars in a stream all follow a similar orbit around the galaxy, they act as tracers of the gravitational field. By studying their paths, astronomers can infer the distribution of mass, including dark matter, in the galaxy that captured them. Tidal streams have been used as a kind of cosmic scale or compass, helping to measure the shape of the Milky Way's dark matter halo. Subtle deviations in a stream's path can even hint at unseen influences, like additional dark substructures. In this way, the ghostly streams serve as tools for probing the invisible architecture of galaxies, linking back to the notion that much of the cosmos is hidden in darkness. Mapping these star streams is like conducting cosmic archaeology. By tracing the path and composition of a stream, scientists can infer what kind of object created it and when the merger happened. It's almost as if the larger galaxy's halo is a history book, with stellar streams as chapters telling of past unions. Each ghostly stream carries information. The chemistry of its stars can tell us they came from a smaller galaxy that had its own distinct story before becoming part of a bigger one. If you were on a planet orbiting a star that is part of one of these streams, your night sky would be spectacular in its own way. You'd be in the far outskirts of a massive galaxy. In one direction, you'd see the main galaxy sprawling across the sky, a glittering metropolis of stars from an outside perspective. In the opposite direction, the sky would open to the deep black of intergalactic space, with only distant galaxies as tiny smudges. The stars around you, the ones in the stream, would be relatively sparse, like an isolated caravan of lights. You might not even realize your star was part of a stream unless you measured its motion. Yet unbeknownst to casual stargazers on that world, they are all travelers together, circling the galactic core as a ghostly chorus, remnants of a departed dwarf galaxy. There is a haunting beauty to these streams. If one could view the Milky Way from afar in a long exposure, you would see delicate filaments of stars swirling around it, barely perceptible, like cosmic whispers. These are the spirits of galaxies past, their light still journeying through space long after their homes have been dismantled. In the silence of the galactic halo, they whisper tales of creation and destruction, of smaller islands of stars subsumed by larger ones. They remind us that galaxies are not permanent islands, but ever-changing, built from the remnants of previous generations. Every tidal stream is a transient feature on cosmic timescales, but while it exists, it serves as a monument to cosmic change. They endure long enough for us to observe them, but given another few billion years, many of today's streams will have dispersed entirely. Their stars will blend indistinguishably into the larger galaxy. Future astronomers, looking at our Milky Way eons from now, might see a seemingly smooth halo and not realize that once there were distinct rivers of stars flowing through it. It reminds us that we are catching the Milky Way in the act of growth, witnessing a phase that won't last forever. We are fortunate to see these streams now, to decode their messages before time erases them. As we drift away from these ghostly star streams, we hold in mind the secrets that galaxies have shared with us, from invisible dark galaxies and shining rings, to missing companions, violent mergers, and ethereal remnants. Yet, our exploration of cosmic phenomena is far from over. The universe holds deeper mysteries and more wondrous anomalies beyond the scale of galaxies, waiting for us to explore. Our journey will continue, moving ever further into the unknown, seeking out the next set of cosmic phenomena that defy explanation under the quiet and infinite night of space. As our cosmic journey continues, we drift further into the quiet darkness between the stars. The vast reaches of space stretch out in all directions, silent and endless. Within this infinite void, one might expect nothing but scattered dust and faint whispers of light from distant galaxies. Yet here, in the emptiness between those great islands of stars, a singular light is moving. A lone star wanders through the dark, untethered to any galaxy, a solitary sun adrift in intergalactic space. This rogue star is a cosmic vagabond, a sun without a home. In the safety of a galaxy, stars usually travel in well-defined orbits, bound by the collective gravity of billions of their brethren. But a rogue star has broken free of those celestial cities of light. It roams the intergalactic wilderness, where the night sky around it would be nearly black. Imagine standing on a planet, if one existed, circling such a star. No familiar band of the Milky Way glimmers overhead. No nearby stars crowd the heavens. Only a few distant galaxies might faintly glow on the horizon of an endless night. The concept is both eerie and awe-inspiring, a beacon of life-sustaining warmth, shining alone in an almost perfect darkness. How does a star become a wanderer, cast out into the void? Astronomers believe these exiled suns were born like any other, nestled inside a galaxy, perhaps in a calm spiral arm or a bustling star cluster. They lived their early lives amid neighbours. But violent events can conspire to fling a star outward with such velocity that it escapes its galaxy's grasp. One common culprit is the gravitational chaos when galaxies collide or pass too close to one another. Picture two galaxies swirling together in a slow-motion dance. As they merge, their immense gravities stretch and pull at each other. Although individual stars are far apart enough to rarely collide head-on, the galactic dance can slingshot some stars away, ejecting them into intergalactic space. In the wake of such a cosmic collision, a handful of stars might find themselves forever separated from their original galaxy, doomed to wander. Another dramatic fate can befall a star that strays too close to the center of its galaxy, where a supermassive black hole lurks. If a binary star system, two stars orbiting each other, drifts into the powerful grip of a galactic black hole, an extraordinary thing can happen. The black hole's intense gravity can rip the stellar partners apart. One star may be captured into a tight orbit around the black hole, while the other is flung outward at tremendous speed. Spat out by this gravitational slingshot, the ejected star becomes a rogue, careening into the great beyond. The Milky Way's core, with its central black hole, is capable of producing such exiles. In 1997, astronomers made a startling discovery using the Hubble Space Telescope. They detected the faint glimmer of stars that were not inside any visible galaxy. One such star was found hundreds of thousands of light years from the nearest galaxy, deep in the intergalactic gulf. This was one of the first confirmed rogue stars, tangible proof that the universe has wandering suns with no galactic home. Since then, scientists have identified more of these stellar castaways. Astonishingly, when we look at massive clusters of galaxies, it turns out a significant fraction of stars reside outside the galaxies themselves. The Virgo cluster, for example, may contain as many as 1 trillion rogue stars drifting in the spaces between its member galaxies. Closer to home, at least several hundred rogue stars have been found in the darkness between the Milky Way and the Andromeda galaxy. Each one is a lonely sun traversing a void we can scarcely imagine. Occasionally, some of these exiles might be gravitationally caught by another galaxy given enough time. Perhaps one day, a rogue star sailing near Andromeda's outskirts will be gently drawn in and adopted. Others, however, will continue drifting for billions of years, moving through the emptiness with only the faint pull of distant galaxies to guide them. The thought of a star alone in intergalactic space invites many questions. Could such a star have planets? If it did, what would life be like on a world orbiting an orphan sun? With no galaxy to provide a mist of background starlight, nights on that world would be truly dark, aside from the steady glow of its one central sun. Life there might gaze at a sky mostly void, perhaps only a distant galaxy's faint smear of light, or the occasional far-off star, would punctuate the blackness. It is a scene of ultimate isolation, a campfire in the deepest night of the universe, Yet it's not inconceivable that planets could orbit a rogue star just as stably as they would around any other star. The star itself remains the same, only its surroundings differ. Perhaps somewhere out there, an orphan star with a family of planets provides enough warmth for a tiny oasis of life, flourishing under a sky devoid of familiar constellations. It is a lonely scenario, but also strangely peaceful. A stable little solar system carried on a quiet voyage between galaxies, unmarred by the gravitational hustle and bustle of crowded galactic life. Rogue stars give us a new perspective on how dynamic and untamed the universe can be. We tend to think of galaxies as tidy islands that neatly contain their stars. But reality is more chaotic. When galaxies interact or merge, things get messy. Stars can be orphaned and flung outwards. Even our own galaxy's future holds such drama. Billions of years from now, when the Milky Way merges with the Andromeda Galaxy, countless stars will be pulled and pushed by tidal forces. While most will remain with the newly formed larger galaxy, some will be ejected into the darkness. Our Sun is unlikely to be among those cast out. It will probably stay within the merged galaxy's core. But other suns will almost certainly be lost to the void, turning into rogues during that grand event. Over time, the Milky Way may gradually shed a small portion of its stars to intergalactic space, like sparks flying from a bonfire. Despite their isolation, rogue stars still shine and follow the natural path of stellar evolution. They burn their nuclear fuel, live out their lifespans, and eventually will die like any other star. Perhaps quietly as a cooling white dwarf, or spectacularly as a supernova if they are massive enough. When a rogue star explodes as a supernova in intergalactic space, it must be an incredible sight. A sudden bloom of light flaring up literally in the middle of nowhere, briefly outshining entire galaxies before fading into darkness again. Such an event would be a rare beacon in the void, a signpost of cosmic upheaval from ages past. The existence of these wandering suns challenges our conventional picture of the cosmos. It reminds us that not all stars stay bound in the communities where they began. Nature allows even stars to become nomads. As we contemplate these solitary travelers, we can't help but feel a mix of melancholy and admiration. A sun without companions is a poignant image, yet there is resilience in its solitary journey. Unbound from any galaxy, these rogue stars wander wherever gravity and time carry them, writing their own chapter in the story of the universe. For now, rogue stars remain a cosmic mystery and a marvel. With each new one discovered, we learn to appreciate the surprising ways our universe works. The universe is not a static tapestry, but a dynamic, ever-changing expanse, where even something as fundamental as a star's home is not guaranteed. One day, trillions of years in the future, long after galaxies themselves have thinned out, rogue stars might be among the last lights shining, tiny beacons moving through a vastly expanded cosmos. They show us that the cosmos still has secrets to reveal, and that sometimes great beauty lies in loneliness. As we leave behind the image of a lonely star traversing the intergalactic night, we return our focus to places where stars gather together. Even among their kin, stars can harbour mysteries. In the dense swarms of ancient stars within globular clusters, we encounter a different kind of puzzle. Not stars cast out into solitude, but stars that stand out for appearing too young in a community of the old. From the depths of cosmic loneliness, we move into the heart of stellar families to explore a perplexing anomaly: the so-called blue straggler stars, youthful imposters in communities of the aged. Inside an ancient cluster of stars, an unexpected sight awaits. Imagine a swarm of stars that has existed for eons, perhaps 10 or 12 billion years. The stars in such a globular cluster are venerable elders, many times older than our Sun, and they tend to shine with a faint red or yellow glow, having long ago exhausted the vitality of youth. Yet amid this community of the aged, a few members burn with a surprising colour: bright electric blue, the hallmark of hot, young stars. These are the blue stragglers, stellar oddities that seem to flaunt their youthfulness in a place where they should not exist. Finding a blue straggler star is like encountering a youngster at a centenarian's reunion. In theory, all the stars in a given cluster formed around the same time, born from the same cloud of gas in a primordial era. They should age together like a cohort of cosmic siblings. As the billions of years pass, the more massive stars rapidly grow old and perish or swell into red giants, leaving only the smaller, cooler stars still burning steadily on the cluster's main sequence. By the current epoch of a very old cluster, no hefty, bluish main sequence stars should remain at all. Those big stars would have lived fast and died long ago. And yet, there they are, scattered here and there in the cluster's crowded core and outskirts, young-looking blue stars among the ancient ones. Their presence is a riddle written in starlight. Astronomers first noted these odd, out-of-place stars in the 1950s, when they plotted the stars of certain globular clusters on a chart of stellar colour and brightness. The vast majority fit neatly onto the sequence expected for an old population. But a handful did not. They were hotter and more luminous, appearing bluer and brighter than the cluster's age should allow. It was as if a few stars had somehow sidestepped the cluster's timeline and refused to grow old with their siblings. Because these youthful stars lagged behind in the evolutionary track, remaining on the main sequence of stellar life when they should have moved on, astronomers dubbed them blue stragglers. They straggle behind in aging, blue when they ought to be red, youthful when they ought to be ancient, given the company they keep. For decades, blue stragglers remained a tantalizing mystery. How could these stars apparently defy the natural progression of stellar aging? Scientists proposed various possibilities. Perhaps these stars were not original cluster members at all, but interlopers that somehow joined the cluster later. That idea lost favour when detailed studies showed the blue stragglers share the same chemical fingerprint as their cluster mates, indicating they were born from the same primordial gas. Attention then turned to ways a star might rejuvenate itself. Could a star effectively reset its clock by acquiring fresh fuel? Two main scenarios emerged to explain how a blue straggler might gain a new lease on life. One scenario unfolds in the intimacy of a close binary star system. In many clusters, a significant fraction of stars are paired off in binaries, orbiting a common center. If one member of such a pair begins to evolve and swell into a red giant, it can spill some of its outer gas onto its companion. The smaller companion star greedily siphons this material, gaining mass in the process. This influx of hydrogen, the prime fuel for nuclear fusion, revitalizes the star. Suddenly bulked up with new fuel, the star burns hotter and bluer, rejuvenated as if it were younger than it truly is. In effect, the star has stolen youth from its partner, like a vampire drawing life from a victim. The donor star, having lost much of its mass, might end up as a shriveled white dwarf, while the recipient shines on as a blue straggler, carrying on the fusion that its companion no longer can. This stellar vampirism is one way to create a blue straggler, by transfusion of fresh life from one star to another. Another possible path to a blue straggler is far more dramatic: cosmic collisions. In the dense heart of a globular cluster, stars are packed much closer together than in our corner of the galaxy. Over many millions of years, chance encounters can occur. Once in a great while, two stars might crash into each other, or even merge. When two smaller, aging stars combine, their joined mass forms a single heavier star. The result can be a hotter, more luminous star than either of the progenitors, essentially reborn as a bigger, brighter blue star. It is as though two dying embers fused to ignite a new flame. In the cluster's context, this collision-born star again looks anomalously young, a blue straggler created by the literal melding of stars. Evidence for both formation mechanisms has been found, and it's likely that both contribute to the blue straggler populations in different clusters. In very dense clusters, direct collisions or mergers might produce many of the blue stragglers. In less dense clusters, the mass transfer vampire star scenario could dominate. A turning point in understanding came when astronomers managed to measure certain blue stragglers in detail. One famous case involved peering into the core of the globular cluster 47 Tucanae with the Hubble Space Telescope. There, a blue straggler was found to be spinning at an abnormally high rate, dozens of times faster than a typical Sun-like star. Such rapid rotation is a telltale sign consistent with a recent merger. When two stars coalesce, they impart their orbital momentum to the new star, spinning it up like a whirlpool. This discovery strongly supported the idea that some blue stragglers are the products of stellar collisions. On the other hand, other studies of star clusters show blue stragglers in binary systems with telltale companions. For example, a blue straggler orbited by a faint companion that appears to be a white dwarf. That fits the narrative of mass transfer. The blue straggler has a white dwarf partner that likely donated mass in the past. In one ancient cluster in the constellation Cepheus, astronomers analysed numerous blue stragglers and found that many had characteristics best explained by the slow siphoning of gas from a companion rather than by head-on collisions. It seems the cosmos has more than one recipe for cheating stellar age. While we now have a good grasp of how blue stragglers probably form, they still inspire a sense of wonder. These stars have managed to extend their youthful vigour against the odds, and in doing so, they illuminate the dynamic social lives of stars in clusters. Far from being static retirement homes, clusters are places where interactions between stars can profoundly alter individual stellar fates. Imagine the environment at play. In a globular cluster, hundreds of thousands of stars are crowded into a ball only a few dozen light-years across. In those cramped conditions, the destiny of one star can become entwined with others. A close pass might strip mass from one star to another. A chance encounter might bind two stars into a binary, or a gravitational dance could end in a head-on embrace. Blue stragglers are the sparkling evidence of these furtive stellar interactions, rarely witnessed directly, but recorded in the renewed vigour of a star that by all rights should have grown old. From the perspective of an observer within a globular cluster, a blue straggler would stand out as a hot, bright blue beacon among the softer glows of its elderly neighbours. If you were on a planet around a normal star in such a cluster, you'd see the blue straggler as one of the most brilliant stars in the sky, piercingly blue-white, contrasting sharply against the cluster's many orange and red stars. It would be puzzling. Why does that one star shine with such youthful intensity in a community where time has aged all the others? This visual juxtaposition echoes the scientific mystery that once baffled astronomers. Over time, we've come to appreciate that blue stragglers teach us how stars can cheat the usual rules by interacting with each other. In the grand scheme, a blue straggler isn't truly young. It's a star that's been reborn or recharged through cosmic coincidences. Eventually, it will age and die like any other star, perhaps ending quietly as a fading white dwarf, or, if massive enough, in a final blaze as a supernova. But for a significant extra span of time, it gets to shine on with renewed youth, seemingly out of sync with the cosmic clock of its surroundings. The mystery of the blue stragglers, once so perplexing, has largely been unravelled by careful observation and clever theory, yet there remains a certain magic to the concept. There is something emotionally resonant about stars that appear youthful beyond their years, as if they have defied time itself. These stars highlight that the universe's order has its loopholes and second chances. A blue straggler is a star with a second chance, a second life, in a sense, granted by the fortuitous intimacy of a companion or the random violence of a collision. As we step back from the glittering throngs of ancient clusters and their paradoxically youthful members, we carry with us a deeper appreciation for the intricate dance of stars. We have seen that even in the apparent stillness of a star cluster, subtle exchanges and dramatic unions can rewrite a star's fate. Now our journey of cosmic phenomena moves from the close communities of stars to the great galactic wilderness, where we will find stars on the move in a different way. Some stars are not content to remain among their brethren at all. They have been flung into high-speed journeys across space. In our next chapter, we follow these restless travelers, the hypervelocity stars, flung from their homes at unimaginable speeds. Far out on the galactic fringes, a solitary star streaks through space faster than anyone ever imagined a star could move. In the vast quiet of the Milky Way's halo, where stars are sparse and darkness deep, this star is a flash of brilliant light racing away from its galaxy. It is a hypervelocity star, a cosmic projectile moving with such extreme speed that it will eventually break free from the Milky Way entirely. Imagine the tremendous energy required to hurl a star out of a galaxy. Yet here it is, a sun travelling so swiftly that the usual bonds of gravity can no longer hold it. Hypervelocity stars are among the fastest moving stars known. To earn that title, a star must be hurtling at hundreds or even thousands of kilometers per second relative to the galaxy, speeds high enough to escape the galaxy's gravitational grip. For context, our Sun orbits the Milky Way's center at about 220 kilometers per second. A hypervelocity star, by contrast, might race along at 1,000 kilometers or more, several times faster than typical stars. That's on the order of millions of miles per hour. At such velocities, a star could travel from Earth's position to the center of the galaxy in only a few million years, a blink of an eye on cosmic timescales. These stellar speedsters make even the fastest rockets humanity has built look like drifting leaves by comparison. The existence of hypervelocity stars was theorized before any were observed. In the late 1980s, an astronomer named Jack Hills proposed that if a binary star system wandered too close to the supermassive black hole at our galaxy's core, tidal forces could tear the binary apart. One star might be captured into orbit around the black hole, while the other would be flung outward at incredible speed, accelerated by the black hole's immense gravitational slingshot. For years, this was a purely theoretical idea. No one had seen an actual star moving fast enough to escape a galaxy. But that changed in 2005, when astronomers discovered the first hypervelocity star. It was found speeding away from the Milky Way's center, just as Hills's theory predicted, at roughly 700 kilometers per second, about 1.5 million miles per hour. This discovery was thrilling proof that nature can indeed produce stars moving at phenomenal speeds. Since that first find, dozens more hypervelocity stars have been identified. They are not easy to spot. From our perspective, they are just points of light, and their extreme motion only becomes evident through careful measurement of their Doppler shifts or their movement on the sky over years. But with large sky surveys and sensitive instruments, astronomers have gradually built a roster of these runaway stars. Many trace their origins back to the Milky Way's center, supporting the black hole ejection scenario. Yet not all follow that pattern, suggesting multiple pathways for a star to gain such velocity. Indeed, recent research has uncovered another dramatic mechanism for launching hypervelocity stars: supernova explosions in binary systems. Imagine two stars orbiting each other closely. One is a massive star that explodes as a supernova. The blast not only destroys that star's outer layers, it also shatters the gravitational bond holding the pair together. The companion star, suddenly freed from its partner's pull, is hurled outward at great speed by the force of the explosion. It's as if one star's death shout punts the other out into space. Astronomers have identified several hypervelocity stars that likely got their enormous speeds from this kind of event. In fact, the fastest hypervelocity star currently known, hurtling at around 2,000 km, over 5 million miles per hour, is thought to have been accelerated by just such a supernova kick. That star moves so swiftly that it defies comprehension. If you could somehow ride along, you'd race from New York to Los Angeles in less than a second. For perspective, even this record-setting speed is only a tiny fraction of the speed of light. Yet for a massive star, it is utterly astounding. What does a hypervelocity star's journey look like once it's launched? Cast loose from its birthplace, such a star will spend the rest of its life traveling through the emptiness of the galactic outskirts and beyond. If it originated near the galactic center, it would rush outward through the Milky Way's dense regions, then punch through the galaxy's disk into the halo, where the grip of gravity weakens. Eventually, if its speed exceeds the escape velocity, the star will break free entirely and become an intergalactic traveler. In a few 100 million years, a hypervelocity star launched from the Milky Way could find itself sailing alone in the intergalactic void, destined to drift indefinitely, unless by some chance it encounters another galaxy's pull eons from now. In essence, these stars are on one-way journeys. Once they've been cast out, there's likely no coming back. For any planets that might orbit a hypervelocity star, the consequences of such a wild ride would be profound. Imagine a planetary system flung along with its host star on a grand cosmic voyage. Night skies on those worlds would change over millennia as the star hurtles through different regions of the galaxy. Eventually, as the star leaves the galaxy entirely, the familiar dense star field of the Milky Way would recede and dim. The majestic band of our galaxy might fade to a small, distant blur. If life existed on a planet around a hypervelocity star, its sky would grow emptier over time as it exits the galactic stage, until only the faint glow of the Milky Way and other far-off galaxies remain as reminders of what was left behind. Could life even survive such an ejection? It's hard to say. The process that flings the star might be violent enough to disrupt any planets. But if some planets did remain bound, one can imagine a lonely civilization looking up and realizing their sun is departing the galaxy, carrying them into the intergalactic dark. It is a poignant image, a solar system cast adrift, moving ever outward through an endless sea of night. One can't help but marvel at the forces required to fling a star at such velocities. Whether through the gravitational might of a supermassive black hole or the titanic fury of a supernova explosion, The result is a star transformed into a cosmic cannonball. Hypervelocity stars remind us that our galaxy is not a closed system. Stars can be tossed out, and indeed some are. In fact, over the eons, the Milky Way will slowly lose a trickle of stars this way, a cosmic shedding that is largely imperceptible on human timescales, but real nonetheless. And just as we lose stars, other galaxies may donate a few to us in return. The vast space between galaxies can be traversed by these hardy stellar refugees. The discovery of hypervelocity stars has opened a window onto some of the most extreme events in astrophysics. By studying them, scientists can infer conditions in the galactic center and the mechanics of supernova explosions. Each hypervelocity star is like a messenger from a dramatic event. By retracing its trajectory and speed, astronomers can often pinpoint where it came from and what flung it. If a star's path leads back to the galaxy's core, it implicates an encounter with the central black hole. If instead a star's motion and composition suggest an origin in a stellar cluster or disk, a supernova kick might be the culprit. In this way, hypervelocity stars carry clues about the violent incidents that set them free. Despite their extraordinary nature, hypervelocity stars also offer a comforting perspective. They underscore how dynamic and surprising the universe can be. Even a star's position in a galaxy is not immutable. The cosmos is ever-changing and full of marvels. Here we have brilliant suns turned into exiles, sprinting through space on solitary trajectories. Eventually, far in the future, a hypervelocity star that has left its galaxy will exhaust its nuclear fuel. Perhaps it will fade quietly as a cool white dwarf drifting in intergalactic darkness. Or maybe, if it's massive enough, it will end in a final supernova flash in the void, a last burst of light witnessed by no nearby observers, a lone firework in the silent dark. It's a lonely fate, but also a testament to the far-reaching consequences of cosmic events. Having followed these stellar daredevils on their race out of the galaxy, we now turn from motion to stillness, from high-speed journeys to the quietest, coldest corner known in the universe. In the next chapter, we encounter a nebula so cold that it has become the chilliest natural place ever found. Our voyage continues from the blazing speed of hypervelocity stars to the eerie, frozen calm of the Boomerang Nebula. Drifting in the darkness, some 5,000 light-years from Earth, is a faint, ghostly cloud of gas and dust. To the eye, it appears as a softly glowing nebula with a curious shape, something like a lopsided bow tie, or as its name suggests, a boomerang. This is the Boomerang Nebula, and it holds a remarkable record. It is the coldest known object in the natural universe. Deep within this tenuous cloud, the temperature has been measured at just 1 degree above absolute zero. That's even colder than the background glow of the Big Bang, colder than the 2.7 Kelvin cosmic microwave background that suffuses space. In this lonely nebula, we encounter cold beyond anything found elsewhere, a chill so extreme that it defied explanation for decades. It was not obvious at first why the Boomerang Nebula is so extraordinarily cold. By all rights, it is a fairly normal scenario, a dying star shedding its outer layers to form a nebula, which is a common fate for stars like our Sun. Planetary nebulae, so named because some of them look round and planet-like in small telescopes, often have striking shapes, and the Boomerang Nebula at first seemed to be yet another beautiful, if irregular example. When astronomers first observed it in the 1980s, they noticed the nebula looked asymmetric through ground-based telescopes, hence the Boomerang moniker. Later, the Hubble Space Telescope revealed a more symmetric, double-lobed, hourglass figure. like two opposing cones of material flowing out from the central star. Many planetary nebulae show such shapes, typically created by jets of gas from the dying star carving cavities in a surrounding gas cloud. The Boomerang appeared to be one more hourglass nebula, yet none of those others are known to be anywhere near as cold. The Boomerang Nebula was doing something unprecedented. It had somehow cooled itself to a temperature lower than the ambient temperature of empty space. For years, this deep freeze was a puzzle. How could the nebula's gas be colder than the faint warmth of the universe's background radiation? The answer, when it came, was both elegant and dramatic. The Boomerang Nebula's central star is shedding its mass at an absolutely furious rate, far higher than in a typical dying star's wind. And that outflowing gas is expanding outward at an extremely high speed. As the gas expands, it cools, much like air conditioning refrigerant gas cools when allowed to expand. In the case of the Boomerang, the gas is moving outward so fast, on the order of 150 kilometers per second, that it has cooled to nearly absolute zero. In effect, the star has produced a gigantic cosmic refrigerator. This ultra-cold outflow was likely triggered by something unique in the star's final stages. One hypothesis is that the central star had a close companion, perhaps a smaller star, or even a giant planet, that plunged into the red giant, stirring it up and ejecting an enormous amount of material in a short time. That would have blasted the star's atmosphere outward in an explosive belch, causing the extreme mass loss and rapid expansion needed to reach such a low temperature. Whether or not a companion was involved, it's clear that the Boomerang Nebula is a transient phenomenon, a snapshot of a brief, violent event in a star's death throes. Floating inside this ghostly nebula is the star that created it, now hidden in part by a veil of its own expelled gas and dust. The star itself has probably shrunk and is on its way to becoming a white dwarf, but it isn't yet hot enough to make the nebula glow intensely. Instead, we see the nebula by light reflecting off dust grains. The Boomerang Nebula's light, as seen through a telescope, is very faint, a pale blue-green tinge in long exposure images, yet it tells a story of drastic events. If one could drift into the center of this nebula, the scene would be one of eerie calm and unbelievable cold. The pressure is almost non-existent, the gas is incredibly tenuous, and everything around is at about 1 Kelvin. Tiny dust particles, strewn through the gas, reflect the weak light of the central star. Because the nebula's core is so heavily shrouded, much of the starlight escapes only in certain directions, creating twin beams that illuminate the lobes of the hourglass shape. Beyond those lobes, the ALMA radio telescope has revealed a more spherical halo of ultra-cold gas extending outward, a reminder that the true structure is more expansive than what we see in visible light. It's a silent, motionless freezer in space, an almost abstract emptiness where heat has nearly vanished. The Boomerang Nebula's deep freeze is a temporary state. In cosmic terms, this phase won't last long. Already, observations show that parts of the outer nebula have started to warm slightly. They are still exceptionally cold, but no longer colder than the cosmic background. As the central star continues to evolve and eventually heats up into a white dwarf, its increasing radiation will ionize the expelled gas and turn the Boomerang into a more typical, glowing planetary nebula. The temperature will rise, and the record-breaking cold will dissipate. In a few thousand years, the Boomerang Nebula will likely lose its singular distinction. It is a fleeting event, a special confluence of circumstances that we just happen to catch. For now, It stands as a fascinating extreme, teaching us that under the right conditions, a dying star can create an environment colder than the universe's background itself. Leaving the Boomerang Nebula's frosty tranquility, we prepare to swing to the opposite extreme of cosmic conditions. From the coldest cold, we journey next to the realm of unimaginable magnetic fury. In our final chapter of Stellar Oddities, we will encounter the most magnetized objects in existence, neutron stars with magnetic fields so immense that they boggle the mind. Steeling ourselves for this next marvel, we depart the quiet cold and set our sights on the magnetars, where the very fabric of matter and space is bent by magnetic forces beyond comprehension. Neutron stars are already extreme objects, the crushed cores of massive stars that exploded as supernovae, packing more mass than the sun's into a sphere only about 20 kilometers across. But among these fantastical stellar corpses exists a special subclass that pushes extremity to an even greater level. They are the magnetars, and they possess magnetic fields so powerful that they defy ordinary comprehension. A typical magnetar's magnetic field is on the order of 10^14 to 10^15 Gauss, a million billion times stronger than Earth's magnetic field. Such numbers are difficult to grasp, but the effects are not. A magnetar's field can twist and stress the neutron star's solid crust, triggering starquakes that unleash bursts of high-energy radiation. The magnetic force can accelerate particles and light to extraordinary energies and reach far out into space. If a magnetar were magically placed at half the distance from Earth to the Moon, its magnetic field would wipe every credit card on the planet clean and disable all electronic devices. At even closer range, a magnetar's field could distort the very atoms in your body. Fortunately, no magnetar is anywhere near us. The nearest known is thousands of light years away. But the mere fact that nature produces such entities is at once terrifying and awe-inspiring. Magnetars were first discovered not by measuring their magnetism directly, but by their dramatic outbursts. In March 1979, detectors on Earth and in space picked up one of the brightest flashes of gamma rays ever recorded, coming from a distant source. The initial burst lasted only a fraction of a second, but carried as much energy as the sun emits in 1,000 years. For another 100 seconds or so, a train of lower energy gamma ray pulses followed. At the time, astronomers weren't sure what they had witnessed. It was unlike typical gamma ray bursts or any known phenomenon. Only years later did researchers identify the culprit as a magnetar. What had happened, they realized, was a starquake on an ultra-magnetized neutron star in a nearby galaxy. The magnetar's crust had snapped under magnetic stress, and in that instant, it released an immense flare of gamma rays. This was humanity's first known encounter with a magnetar's fury. Since then, other magnetars in our own Milky Way have been observed to flare in their turn. On December 27, 2004, a magnetar on the far side of our galaxy let loose a burst of energy that was detected by spacecraft and observatories across the solar system. For a brief moment, this magnetar, some 50,000 light-years away, was the brightest source of gamma rays in the sky. It bombarded Earth's upper atmosphere with a blast of radiation, causing a measurable disturbance in our ionosphere. Were a magnetar flare of that magnitude to happen much closer, the effects on Earth would be devastating, but at the distance of tens of thousands of light-years, it was harmless, serving mainly as a spectacular cosmic light show. These flare events are exceedingly rare and short-lived, but they offer a window into the tremendous energies stored in magnetars' magnetic fields. What makes a magnetar so magnetic? Scientists think that on rare occasions, when a neutron star forms from a supernova, the combination of rapid rotation and convection in the newborn neutron star can amplify the magnetic field to colossal levels, a sort of cosmic dynamo working at peak efficiency. Perhaps only 1 in 10 neutron stars is born under those special conditions, creating a magnetar. The rest have normal, strong magnetic fields that are far less intense. Magnetars shine brightly in X-rays and gamma rays for a brief span of time, maybe 10,000 years or so, as their magnetic fields power their emissions. After that, the field likely decays, and the magnetar settles into a quieter existence as an ordinary neutron star or pulsar. Because of this short, active lifetime, magnetars are relatively rare. Astronomers have catalogued only around 30 in our galaxy, and each new discovery is an event, a combination of detective work and good fortune. To imagine a magnetar up close stretches our imagination to its limits. Picture an object the size of a city, but with more mass than the Sun, spinning perhaps once every few seconds. Around it, invisible yet potent, is a magnetic field that would make a compass needle on Earth spin crazily. Not that a compass could survive anywhere near it. The field lines around the magnetar trap plasma and whip it around, forming a magnetosphere like an oversized version of Earth's, but vastly more powerful. The very space around a magnetar is affected by its magnetism. In fact, near the magnetar, the vacuum itself behaves in strange ways. Quantum effects cause light to become polarized and split in a phenomenon called vacuum birefringence. The magnetar's surface is a solid crust of atomic nuclei and electrons locked in crystalline arrangement by the immense gravity. Yet even this hard crust can crack under the strain of the shifting magnetic field. When it does, the magnetic field reconfigures explosively, and a torrent of high-energy photons erupts from the star's surface. These outbursts are the magnetar flares we observe across the galaxy. Despite their fearsome qualities, magnetars captivate astronomers because they represent physics at the extremes. The densities, fields, and energies involved are so far beyond normal experience that magnetars serve as natural laboratories for exotic physics. By studying magnetars, scientists test theories of how matter behaves under intense magnetism and gravity. Every new observation, a periodic pulse of X-rays here, an unexpected flare there, is a clue to the inner workings of these magnetic monsters. We marvel that a 20-kilometer object can affect its surroundings across many light years, and that a single starquake on a magnetar can release more energy in an instant than our sun will in 1,000,000 years. Magnetars also fire the imagination. In the darkness of space, a magnetar wouldn't look particularly menacing from afar. It might appear as just another faint neutron star, perhaps detectable only with X-ray or radio telescopes. Yet beneath that quiet exterior lies a magnetic fury that could wreak havoc if you were close. One analogy is to think of magnetars as cosmic sleeping dragons. Most of the time they slumber, emitting steady X-ray pulses as they spin. But occasionally they stir, and when they do, they breathe fire in the form of gamma-ray bursts. If you were nearby, it would be like a dragon's breath igniting the very space around you. As we conclude our exploration of these stellar oddities, from rogue stars wandering alone, to blue stragglers cheating time, to hypervelocity stars racing away, to a nebula colder than deep space, and finally to magnetars with their unimaginable forces, we're left with a profound sense of wonder. The cosmos is rich with phenomena that challenge our understanding and stretch the bounds of what nature can do. Each of these cosmic marvels reminds us that the universe is more inventive and extreme than the simple textbook scenarios. And yet, for all we have seen, the journey isn't over. Beyond these wonders, more mysteries await. In the next part of our documentary, we will venture further into the unknown, continuing our voyage through a universe that ceaselessly surprises and inspires those who explore it.